4, find the number of ways to reach the k's stairs. So we are giving a non-negative integer k, and this k can be 0 to 10 to the power of 9. We can check it from here. And there exists a staircase with an infinite number of stairs. Yeah, we don't think, basically we don't need to understand these errors because it will have no influence to our questions. We just will say that there will be an infinite number of stairs, and with the lowest stair number gonna be 0. Yeah, it means the stairs can never be less than 0, and Alice has an integer jump, and with an initial value of 0. So this jump from the beginning, it is 0. So this jump can become so she starts on stair 1 and wants to reach stair k using any number of operations. So this means the operation is unlimited. If she is on stair I, in one operation she can do. So this is for the different cases. So Alice can go downstairs to I-1. If she goes downstairs, she cannot go downstairs once more because this operation cannot be used consecutively or stair 0. Yeah, so this means if Alice, so for example, if I cannot use drawing, but I think it is okay to explain. Yeah, so this operation cannot be used consecutively. This means if I use I-1, for the next time I cannot use I-1 or stair 0. So this means if I'm on stair 0, I cannot use I-1. Yeah, so there are two different cases. Cannot be used consecutively or stair 0. Yeah, this description is a little bit misleading, I think, but I think it is still okay. Go up to stair I plus 2 to the power of jump, and then jump becomes jump plus 1. So another way is to go up to stairs I plus 2 to the power of jump. Jump is just from beginning, and the jump is 0. So if we did this operation one time, and the jump will be updated to jump plus 1, we're going to return the total number of ways Alice can reach stair k. Note it is possible that Alice reaches the stair k and performs some operations to reach the stair k again. Yeah, so this just means Alice can jump for different cases. So for example, it's just an example. Maybe 1 to 3, 3 to 1, this is one case. Another case maybe 1 to 2 to 3 to 2 to 1. Yeah, so it's gonna have two different cases. It's not one case. So these are the two different cases. This is just an example. Yeah, because the operation is gonna be different. Basically, we only have two operations, I-1 and I plus 2 to the power of jump. Yeah. Now, what we are given, so we start at stair 1, and we want to reach stair k. So this basically is a dynamic programming problem, but we can use DFS with memorization to make it easier for coding. So we're gonna prepare a DFS, and finally, I'm going to return this DFS. So we need to design this DFS. So from the beginning, we are at stair 1. So we're going to prepare a stair 1. And we also need to prepare the jump. From the beginning, the jump is 1. And then we're going to update the jump. Yeah. And I think we also need to prepare, I will call it has reversed or not. Yeah, because has reversed is a state. I have to check if I has reversed or not. If Alice go backward, use this operation, it means she has go backward one time, has reversed one time, has go back, or we call it go back. Yeah. Let me call it or we call it go back. Yeah. So if she go back one step, so this means she cannot go back anymore. She must go forward. Use another operation, I plus 2 to the power of jump. Yeah. So basically we need 3 variables. So this one gonna be from the beginning. So this is fixed, and then this 1 will go to this number k, and the k gonna be a really big number, 10 to the power of 9, and this is 0. Yeah, I've already forgot, so let's just write it. So this is the stair, so the stair 1, and the 0 is the jump. Yeah, so this jump will be updated to 1 time after using this operation, but we are not sure how many times. And we still have a go back. It's gonna be a boolean value, true or false. Yeah, so for this go back, let me just put it here. So from here, I'm gonna use I. This I gonna be a number, and I will use a jump variable, and I will use this go back. And for the go back here, I will give a false from the beginning, because from the beginning I didn't go back. Yeah, until I go back, I will make it to be a true. Yeah. Now let me just copy it to here. Yeah. Now I think we can start to check. So what is the true case? So if this I equal to k, I can return a 1 plus something, but I will write it later, because if I return a 1, I'm gonna stop the recursive function immediately, but I cannot stop it. Yeah, because it is said it's gonna have different ways. Yeah, even we find a solution. So for example, k equal to 0, maybe 1 to 0, we find a solution. We cannot stop it immediately. We have to check different cases. This is according to the example. Yeah, Alice starts at stair 1, using this operation can reach to 0. Alice starts at 1, using this operation can reach 0. Even if she reaches 0, she didn't stop. She can still do some other operations to reach 0 again, and this is also another way. Yeah. So this is why we cannot stop immediately. We have to plus something, and this is something gonna be a DFS. Yeah, so we're gonna put it later. Now I'm gonna prepare a result array. Basically, I need to check if I equal to 0. So this is the case if Alice at stair 0 or go back. This means yes. So the state. So the previous state for the Alice, yeah, just to go back. If Alice go back, this means Alice cannot go back again. Yeah. Now what we can do? Result should plus equal to DFS. Yeah. So if it is a 0, so Alice can only choose the second step. So it's gonna be I plus 2 to the power of jump. And this is going to be updated to this I. And what about the jump? Yeah, so if we did this operation, the jump would be updated to jump plus 1. Yeah, and if it is this 0, or if go back is true, yeah, this means for the next time it's going to be a false. So this means Alex can choose 2 directions, go backward and go forward. So this is backward and this is forward. So yeah, except those 2 cases, it's gonna be the second case. So and we only have this. Yeah, what left behind is only the case. It can be I more than 1, or this go back is true. Yeah. So this means definitely I must be more than 1, and go back must be true. And we cannot find any other cases. Yeah, because this one actually include I equal to 0. Yeah, if I equal to 0, we're gonna execute. This means I definitely not equal to 0. Yeah, and definitely go back equal to true. Yeah, so if it is like that, so the result would plus equal to. We're gonna check the 2 different cases. So first of all, Alice can go back. If C goes back, it's gonna be I yeah, if C goes back, it's gonna be I minus 1, and the jump would be the same. And then if C goes back, so it means the go back state is true. Yeah, so here gonna be true, and plus another one. I think we can copy it from here. Yeah, so another way is to just go forward. Yeah, if it goes forward, it's gonna be the false. Only if it goes back, we're gonna set it to true, because if we set it to true for the next time, Alice can only go back, can only execute this line. Yeah, but if it is false, so it means Alice can execute 2 different ways. Yeah, so if they go back, it's going to be I plus 2 to the power of jump, and the jump would be updated to jump plus 1. Yeah, and finally, we need to return the total number of ways. So we're going to return the result. Yeah. Now we need to finish this area, because if we didn't do it, we're going to make a mistake. Yeah, let me just try to check if everything's okay. But before that, we can have trimming, otherwise we cannot pass. So the trimming is that if this I, yeah, if my number is more than k plus 1, if this number is too big, I'm gonna return a 0. Yeah, so this means for I, if I equal to 2, for example, but k plus 1 equal to yeah, let me use I equal to 4, maybe k plus 1 equal to 3. So for example, k equal to 2, but I equal to 3, it is still okay. But if I equal to 4, it is not okay. This means if k plus 1 equal to 3, yeah, this means k equal to 2, I equal to 4, definitely it will not work, because only the difference of 1 is okay. For example, 4 and 3 is okay, but currently k equal to 2, so k plus 1 equal to 3. Yeah, so this means from 4, yeah, let me try to explain. If this I is 4, so if this 4 is more than, yeah, if this 4 goes too far away, and this 4 can never go back. If the difference is 1, for example, k equals to 2, it is okay. Yeah, we can still go there. If k equal to 2, if k equal to 2, I equal to 3, we can still go there. Yeah, because I can use I minus 1, can still go there. But what if equal to 4, we can never go there, because I minus 1, it is 3, and for the next step, it's gonna be 3 plus 2 to the power of jump, and the jump gonna be at least 0. It's gonna be 4. Yeah, so we can never make the number smaller to get it to be a 2. It will never work. So this means we need to check I should be more than k plus 1. If it is more than that, we're gonna return a 0. But currently it's gonna be it is not right. Yeah, because while we are using the memorization, we cannot stop from here immediately. Otherwise, if you don't want to use memorization, maybe you want to use self-dot count plus 1, but that will not work because this is not memorization. If you, yeah, that will be time limit exceeded. But if you want to use the case, and from here you need to plus something. But let's just check if we don't plus something. Yeah, so it is false. Of course, it is false because we added it too early, or maybe we want to prepare a self-dot count from here gonna be 0. We will not use cas. We're gonna use backtracking or DFS. Definitely it will not work. And from here we will use self.count plus equal to 1, and here we just delete these areas because we want to use backtracking, and we're gonna delete all these areas, and this is backtracking. Yeah, we just do the backtracking to check how many different ways. Yeah, as you can see, it works, but it cannot pass for all testing cases because we didn't use cas. This is wrong. Yeah, this is even we get it wrong. Output should be expected for. Yeah, normally it should be okay. I don't need this one. Yeah, maybe I would to make it right first. Let me check. I think I need to use the cas, and from here I need to return 1. I cannot stop it too early, so it's gonna be this one. So I need to check if I equal to 0 or go back is true, else it will be 1 plus this one. I think I need to set it to be 2 line. Set it to rapid. Yeah, now let me try to run it. Yeah, now it works. Yeah, so my idea is that if we were to use the DFS with memorization, we cannot stop it too early, but we need to plus the different cases. Yeah, even we get a result of 1, but we need to plus the first case is that if this I equal to 0 or go back, the first case we need to still plus these values, else we need to use another way. It's gonna be 1 plus this cutover values. Yeah, because we still need to execute. Yeah. Now let me try to submit it to check if it works. Yeah, as you can see, it works and it's pretty fast. Yeah, I want to produce a wrong case actually. I didn't get it right. I want to get a time limit exceeded cases. Yeah, I think we can use another way to produce a wrong case. And for this case, it's difficult to calculate the time complexity. I think I'll go back. Yeah, because this I to k plus 1 is difficult to calculate, I think. This I is 10 to the power of 9 to this k. I think it is log n. Yeah, definitely it is log n time, because for each of the step, we will ignore about this I minus 1, because for each of the step we can have 2 different cases, I minus 1 or this one. But for calculating the time complexity, we're gonna use I plus 2 to the power of jump. So I think it's gonna be log n time, and log n is 10 to the power of 9. Yeah, 10 to the power of 9. This is log n, And what about this jump? Yeah, because we yeah, so for this jump and I, it is log n, and this go back is just true or false, it doesn't matter. So I think the time complexity should be log n time. Yeah, because I didn't find any for loop. And for this I and equal to k and this jump, yeah. So I think the time complexity should be log n time. Now we want to find some other. Yeah, maybe we can use backtracking. But what if we don't know about this one? What are we gonna do? So here we're gonna prepare a self.answer maybe plus equal to 1, and here we're gonna delete the result, and for here we're gonna go for the backtracking, and if else yeah, we're gonna go for the backtracking about this one. So here yeah, I'm not sure, maybe elif go back, we're gonna go backtracking. Maybe we can only write it like this, and we're gonna delete these areas. We don't need the class, and this will become the backtracking. Yeah, we're gonna check how many different ways. So we're gonna delete this one, and self.answer should be 0, and finally we're gonna return self.answer. Yeah, I just want to check if the backtracking works okay or not. Yeah, as you can see, it works. So this is the backtracking, but it's gonna be time limit exceeded. Yeah, because this is not a backtracking problem. We needed to use a memorization by DFS to solve it, and basically it is the dynamic programming, but we cannot use backtracking. Yeah, because even as you can see, it is a time limit exceeded. It seems it passed a lot of testing cases, but it did not work because this is not backtracking. If it is backtracking, the time complexity would be really large. Yeah, it is not log n time. Because all the values, we didn't store any of the values, and we have to repeat the calculation. Yeah, but if we write the backtracking like this, if I equal to 0 or go back, yeah, or go back, we're gonna execute this line. Yeah, let's just check if it works. Yeah, it also works. Yeah, because it's the same. Yeah, because of each of the time, definitely we're gonna backtracking for this one. Yeah, but still it's gonna be time limit exceeded. Yeah, it's nearly the same. So yeah, so I think that's for today's problem. So this means yeah, for some of the problem we have to use dynamic programming to solve it. Yeah, and we have to prepare something like this if we were to write DFS, or you can write it differently, but you cannot stop it immediately from here. You cannot return a 1 immediately. Yeah, now let me just submit it again to prove it should be okay. Yeah, so that's for it. Thank you for watching. See you next time.